Now, before we talk about Green's theorem, what I need to do is just make sure we understand the different types of curves that I'll be referring to. And I'll just draw those up here. This is very simple for you. If I have a curve like this, look at that curve, okay? That curve is closed. And we say it's closed because, I mean, for obvious reasons. If you contrast it with this, that curve is not closed, okay? So we say this curve is closed, and this curve is not, not closed. Now, so in other words, it's closed if you pretend you're trapped in there and you can't get out. Well, that's an indication you have a closed curve. In other words, it maybe starts here and it ends here, so it's closed. Now, there's another term that we want to use, and that is this is a simple closed curve. So this right here is simple. And this one is also simple. It's not closed, but it is simple. This is a closed, simple curve. Now, to help you understand what we mean by simple, let me draw a closed curve that's not simple. This one, that's not simple. And it's not simple because it crosses itself. A simple curve does not cross itself. So this is closed, but not simple. That's the way that goes. Now, so, I mean, it's kind of intuitive when you hear the names. Now, you can have a curve that's not closed and not simple. It doesn't have, you can have something like that. That's a curve that's not simple and it's not closed. All right? Now, what we're going to look at is a simple closed curve with a particular orientation. Remember, when we talk about a curve, we're concerned about, well, how is it oriented? If you trace out this curve, which way is it traced? And in particular, we're going to concern ourselves with clockwise, counterclockwise. If you have a curve, let's suppose that you have a curve like this, and it's oriented this way, where it's traced out counterclockwise. This is a simple closed curve that's counterclockwise orientation. In other words, if you were walking in the direction that this curve is traced, looking over to the left, you have this region. Okay, it's always on your left. Now, this is a simple closed curve, and we're going to look at a line integral over a simple closed curve, like that. Okay? So, I've drawn this out in advance to show you, how we're going to approach Green's theorem. We have a vector field, and then we have a path through the vector field. So here is the vector field, F, Mn, and the M and N are both functions of x and y. And you can see here on this first graph right here, notice I've got exactly the same, it's exactly the same as this one over here. So this is exactly the same curve, and you have exactly the same vector field. So what we're going to look at is we're going to look at this line integral right here. Okay? Now, notice I put the little circle on the integral indicating that you have a closed curve. Okay? So what we want to do is we want to look at evaluating a line integral through a closed curve like this that's oriented as you're walking around it where the region is on your left. So we're going to look at evaluating this line integral over that curve. Now, so what I'm going to do is look at this form of the line integral right here. Okay? See, I've got this form. And I'm going to break it apart. The first thing I'm going to do is I'm going to look at the dx part right here, the dx part, and then I'm going to look at the dy part over here. That's what I'm going to do. And so, first of all, let's look at the dx part. And to look at the dx part, now what I'm trying to do is just show you, I'm working toward, it's kind of like when you were shown the quadratic formula. You kind of derive it by completing the square, and you get to the point where you say, oh, I see where this came from. So that's what I'm trying to do here. I'm trying to derive Green's theorem, or kind of, it's not really a proof because this is kind of a special case. But let's look at this first graph here. And what I've done with this first graph to deal with this mxy dx is I've got this curve and I've partitioned it. I've partitioned the first curve and the second curve, even though they're the same, in two different ways. For this first one, I've got g1 of x being this yellow part down here, okay? And then g2 of x being this curve up here. So in other words, I've got c1 and c2, and what I'm going to do is I'm going to add those two. I'm going to do the integral for c1 and the integral for c2 and add those up, and that will be all of c. Now, another thing I've done is I've said, okay, this bottom curve is some function of x. And the top curve is some function of x. I'll call the bottom one g1 and the top one g2. And that's what my y is, okay? So y is a function of x. So let's see what this looks like then. Here's what we're going to do. We're going to take this integral, and I'm going to split it up. And the first thing I'm going to do is I'm going to go from a to b. Now, I get a to b from right here. See, I've got a, I've got a right here and b right here. So I'm going from this starting point over here to this ending point. Okay? Now, so I'm going to integrate from a to b. And what I'm going to do is I'm going to take this function m. X is going to be what x is, but y is this g1 of x. And there I have that, right? Does everybody see that? Now notice I don't have the little circle around it here. I'm just going from a to b. This is just a regular integral now, really. Okay? Now let's add to that the second one. The second one, I'm going to pick up where I left off here and go from b to a. And this is going to be m of x g2 of x dx. Okay. Does everybody see that? So I'm just adding these up, right? Now, if you put these together, you'll see what I did. I've got C1 and then I've got C2, right? Any questions about that? Now, I don't particularly care for this idea that I'm going from B to A. So let me make some changes here. Here's what I want to do. I want to rewrite this whole thing. I've got my integral from A to B of mx g1 of x dx minus A to B. Now see, this went from B to A, but now I'm changing it from A to B, and I can do that as long as I put a negative out front. So this is going to be mx g2 of x dx. Okay? Is everybody dandy with that? Is that okay with everyone? Okay, now I can of course put these together now, because in both integrals I'm going from A to B, and I can put them together as one integral. There's nothing to stop me now. So I've got this. I've got the integral from A to B of m of x g1 of x minus mx g2 of x and all this dx. We just got a regular integral here. Okay. Any questions about that? Now, I think I want to do one more thing. I think what I want to do is pull a negative out of here, because and this is just because I want it to look a little different. I don't like the G2 being over here. I like the G2 being out front because it is the top one, right? See, here's G2 up here. There's G2. So I'm just going to do another trick here. I'm going to pull a negative out. And if I do that, here's what I get. I get the integral from A to B of mx g2 of x minus mx g1 of x. Yeah, that's the ticket. There, how's that look? Any questions about that? So, I mean, I've not done anything special here. I'm just kind of playing around with the properties of integrals. Now, I want to look at something else here. Look at this. You notice that I could rewrite this way. I could say, well, this is going to be mxy as y goes from g1 of x to g2 of x. Isn't that right? Y'all see that? I mean, just using this notation, you can see that I could represent this as this. And I'm just putting in G2 in for Y. You know, this is Y and this is Y. Okay. Any questions about that? Okay, now, one more thing I want to do with this thing. If I do this, just think about this. Can I do this then? If I go from A to B, and inside here, I'm going to do this. I'm going to put the antiderivative, or I'm going to do this. I'm going to do the partial of m with respect to y, like that. I can do that, right? In other words, and if I do this, if I put another integral in here and say g1 of x, g2 of x, and then I have this, I have d, well, let me just put dA here. This is going to be the same, right? In other words, if I integrate this with respect to, if I integrate this, and I could go ahead, let me just go ahead and put dy, let's say dy and then dx, right? I can do that, right? That's saying the same thing because m is the antiderivative of the partial, right? Ah. Yeah, there's a negative in front. Okay, well, now let's do this. Let's generalize a little more and just say this is negative, and I'll just put an r down here, and I'll put partial m with respect to y dA. That works, right? So these are equal, right? Okay, any questions about that? Now, so what I've done is I've just taken, I'm looking at this line integral above, and I just said, well, let's take the first part of it and see what we can do with that. And here's what I got. I got that, okay. Now, let's go back up here and revisit the line integral overall, this one, okay? We're looking at this thing overall, and now I'm going to take the second part of it. I'm going to take this part right here. And for that part, I'm going to use this same curve. I'm not changing my path at all. I'm using the same path through this vector field, same vector field. But now I'm going to just change the way I break the curve up. Now here's what I'm going to have. I'm going to have in yellow over here, in yellow is C1. And that is a function, its x is a function of y. Okay? So x equals h1 of y. Now over here, x equals h2 of y. And that's my C2. So what I'm doing now is I'm breaking this path up just a little bit differently. And let's see what we're going to get when we do that. If I can rewrite this now this way. I'm going to integrate, and oh, by the way, I'm going from alpha to beta here. And I chose alpha and beta just because I want it to match up with A and beta to match up with B. But let's see what we can do here. Okay. I'm going to integrate this first curve. And it looks like it's going from beta to alpha. Is that right? And that's going to be n, but in place of x, I'm going to put h1 of y. And then, whoops, and then I'll just leave y the way it is. Okay, so that's the first part, right? I went from beta to alpha because I'm looking at starting right here and just going all the way over to here. So beta to alpha. Okay. Any questions about any other questions? Okay, now what I want to do is I'm going to go from alpha to beta with the H2, right? Because I'm oriented in the Y, right? Okay. So now let's do this. So I need to add on to this. I'm going to go from alpha to beta n of H2 of y dy. Okay, I think I got that right. Any questions? Okay, now, so what I did was exactly what I did before, only now it's a little bit harder to see because we're not used to thinking of functions of y, right? We're used to thinking of functions of x. Okay, now I'm going to just play around with this now a little bit. I don't like going from beta to alpha, so let me just factor out a negative out of that. And I'm going to get this. I'm going to get negative alpha to beta in H1 of y. And then let me just go ahead, now that these are the same, well, let me just go ahead and put this. Alpha to beta in H2 of y dy. Okay, so just change changed it from beta to alpha to beta. Now, let's look at this then. If I put this together now, there's nothing to stop me from putting this together. Here's what I have. I have negative, whoops, let me not put the negative there. Let me do this. I'm going to have this. I'm going to have the integral from alpha to beta of n of H2y minus n of H1y dy. See, I put the negative in the second part. Okay, how does that grab you? Now, we're playing the same little reindeer game we played before, right? We can now change this to say, well, I've got alpha to beta, and this is going to be n of x, y, and x is going from h1 of y to h2 of y, and then I've got the dy over here. Now that says the same thing, right? And this is x, right? Okay, does everybody see that? Okay, then let's go to the next step then. So the next step is we've got alpha to beta, and let me do this. Let me put another integral in there. I put h1y, h2y, and let me do the partial of n with respect to x this time, right? And here's dx, dy. Okay. Everybody okay with that? I'm just rewriting what it is, right? Okay. Now, let's see what this is going to give us. If we redo this, here's what we've got. Whoops. Here's what we've got here. Erase it. We've got this thing. We've got the integral over that region is going to be the partial of n with respect to x, and I'll just do dA. Okay. Now, remember, this is the second part of that, right? So this is the end part, the vertical part of that line integral. So we've got a couple of things here. We've got this one, and we've got this one right here, right? We've got these two parts. Now let's see if we can put them together. So I've got this line integral, and over that region, and both of them are the same curve. And we have m dx plus n dy. Now, we know what m dx is. It's this thing, right? This first thing. So here's what we have. Here's what we found. Just putting in the parts here, what I'm going to have is I'm going to have the double integral of, and let me put this in first. Partial n with respect to x minus the partial of m with respect to y. Okay? Everybody see that? Any questions about that? So I just put the two together. I worked with this line integral a part at a time. I broke it in two parts and just did different paths. I mean, the same line, the same path, but I broke the path up into different parts. Any questions about that? Now look, it looks like what we're saying is if we do have this particular type of line integral and it's oriented counterclockwise and it's simple and closed, it looks like what we're saying is that this line integral, now remember this is a line integral for a vector field, it looks like we can solve it this way. The partial of n with respect to x minus the partial of n with respect to y, just use a double integral. It looks like that's what this is saying. Well, this is Green's theorem. It gives us a way that we can evaluate these line integrals, and it's pretty interesting. It's a pretty interesting result here, but let's look at an example. And I've drawn this out in advance to save us time. This is a closed curve, simple closed curve. It's oriented counterclockwise. And what we want to be able to do is we want to be able to evaluate this line integral over this closed region. Now, I'm going to do it two ways. I'm going to do it the old way just so that we'll see, without Green's theorem, just so that we'll see, oh, I see how this, just as a refresher on how we evaluate line integrals in the first place. Now, I've already written the vector field. I've already written the integral here. Now, what I'm going to do is I'm going to look at the first curve. I'll just refer to this as C1, and this over here is C2. So I'll do C1 first. So here's what we've got. For C1, we are going to, I have 5x, and in place of y, I'm going to put x squared, and then I have dx. Okay? So there's the first part, right? So what I did was, because y equals x squared, that's C1, right? So what I did was, in place of y, I just put x squared. Now, you could parametricize this whole thing and use, you don't have to do it this way. But this is, I think, a little bit simpler way. Now, we have x cubed, and I need to put in something in place of y, dy. So remember, in this particular curve, we've got y equals x squared. Then dy equals 2x dx. Okay? So in place of this, I'll put 2x dx. That's what I'll do. Now, this is for C1 right here, right? This is for C1. Now, I'm going from 0 to 2. Now, I'm going to do this, and then I'm going to put the other one, and then I'll put them together, because you realize this is only part of the answer. So let's see what we get when we go through this. This is, now it's very simple integral, 0 to 2, and we've got 5x cubed plus 2x to the 4th. Now, if you see me mess up, let me know. Because at this point, now it's just going to be a careless mistake. Okay, 5x cubed plus 2x to the 4th. And now let's put that in and see what we get. We get 5 over 4 x to the 4th plus 2 over 5 x to the 5th. And we're going from 0 to 2. Okay, any questions? Now, let me know if I mess up here, because I could easily mess up. Now, if, of course, we don't have to worry about the 0. So we've got this. We've got 5 over 4 times 2 to the 4th plus 2 over 5, 2 to the 5th. And of course, 2 to the 4th is 16. So this first one's going to be 20 plus 64 over 5, I believe. Isn't that right? So I think if we work this out, this will be 164 over 5. Okay. Everybody good with that? Okay. Now, let's go ahead and look at the second one. So I'm going to now look at the second curve. And I set it up the same way, except now I'm not going from 0 to 2. I'm going from 2 to 0. Okay? See, it matters how this curve is traced out. So I'm going from 2 to 0 because the idea is you're going up this curve and then down this curve, right? So you're not going from 0 to 2. You're going from 2 to 0. Now I've got y equals 2x. So let's see what we've got here. If y equals 2x, then dy equals 2 dx. So something to keep in mind there. So now let's remember what our function was. Our function was 5xy. So here we go. We've got 5xy dx. And what was the other one? X cubed? Was that how it went? Like that? Okay. So let's see what we've got now. Okay. 2 to 0. Okay, so this is 5x times 2x dx plus 3, no, not 3x squared. I started to differentiate at the wrong time here. X cubed. Now, in place, we put a 2 dx. Okay? Now, did I do everything correctly there? In place of y, I got a 2x. In place of dy, I got 2 dx. Okay, so that looks good. Now, I'm going to... It's irritating to have the 2, 0 like this, so let me go ahead and call that negative 0 to 2. And then I can work this out. This is 10x squared, okay, plus 2x cubed. And then this is just an elementary school integral, right? Okay, so let me just make sure. Now that I said that, I'll mess up on it, right? Okay, so that's 2x cubed. Now, let's see what we've got here. This is going to be 10/3 x cubed plus 1/2 x to the 4th. We're going from 0 to 2. Okay? Yeah, and there's a negative in front. Yeah, there. See, I knew I would mess up. And I did. I was right again. Okay. Now, let's go ahead and see if we can work this out. So this is going to be a negative 10/3 times 8, right? 2 to the 3rd power is 8, plus 1/2 times 16. Yeah, and that's that. Okay, let's see what this is going to give us. So we're looking at big numbers here. This is going to be 80 over 3 plus 8, right? Now, that's going to be, let's see here, negative 80 plus 3 times 8 is 24. So what is that? 104 over 3, negative 104 over 3. Okay? All righty then. Let's go back up. So we got to add 164 over 5. So here's the grand finale. 164 over 5 minus 104 over 3. Okay? And we add those together, and let's see what we're going to get here. This is going. It looks like the common denominator is 15, so this is going to be 3 times 164 minus 5 times 104 over 15. Did I do that right? And what do you get when you do all that? Somebody, what is the top? What does that add up to? Like 20 something, right? Like 28, is it? Something like that? Anybody got an idea? Okay, so it looks like we got negative 28 over 15. Yeah, there you go. Now, that's the old way of doing it, right? That's the old way of working through a line integral. That's without Green's theorem. Now, let's look at Green's theorem, because what Green's theorem is going to have us do is it's going to have us take the partial with respect to x of this y component. Whoops. Whoops. Let me get this. The partial with respect to x of the y, and minus the partial with respect to x of the partial with respect to y of the x component. Okay. Now, so let's go ahead and set that up. Now, if I set up my integral, let's think about how this integral is going to look. Okay, so we're going to have this thing. Now, so we're going to take the partial with respect to x of x cubed, right? Minus the partial with respect to y. And what was that part? It was 5xy. Is that what that was? Okay. I think I got this right. Now, we can go back and look at the theorem that the partial, there you go. Looks like we got it. Okay. Now, let's see what this is going to turn out to be. If we look at this, and I'll put in the bounds here in a minute, but this is going to be 3x squared, that, minus, now the partial with respect to y, so this is going to be 5x, isn't it? Okay. Now, I think what I want to do is I want to integrate with respect to y first. Okay. Actually, let's see. We're right back down to working with just a double integral now. And I think, well, let's see. Let me integrate with respect to, the way this is set up, I mean, everything's in terms of x, right? So I'm going to, here, let's go ahead and see here. Okay. So I think I can integrate with respect to x first. Since I guess I could, integrate with respect to x and then y. So what does x go to? If you look up here at this one. Yeah, y over 2 square root of y. So let's do this. Okay, so it goes to y over 2 square root of y. And then what does y go to? 0 to 4. That's right, 0 to 4. Okay. Now, this should give us the same, it should give us what we're looking for. It should give us the same, it should give us negative 28 over 15. Okay? Okay, so let's see what we've got here. We've got 0 to 4, and now I'll integrate with this. So this is going to be x cubed minus 5 halves x squared, and x is going from y over 2 to the square root of y. And then I've got dy here. Okay. So there's what I have so far. Now, let's go ahead and continue on. Okay, so that's going to be 0 to 4. And I'm going to put in, of course, the square root of y. So this is going to be y to the 3 halves, right? Minus 5y. 5 halves y, isn't it? Okay, so I just put the square root of y in. Minus y cubed over 8. And then 5 halves y squared over 4. And all of that dy. Okay, is everybody okay with that? A little bit messy. Hopefully it comes out right, though. Okay, now let's see what we've got. Okay. I've got 0 to 4, and I'm just going to try to clean this up a little bit. There's 3 halves minus 5 halves, y minus y cubed over 8. And then putting these together, I'll get plus 5 eighths y squared dy. Now, provided we've done everything correctly, this should go pretty smoothly, right? Okay. So let's see what we've got here. First, this first integral, this is going to be 2/5 y to the 5 halves, right? This first one, because 3 halves plus 2 halves, 5 halves, minus 5/4 y squared. Okay. Plus 5 over 24 y cubed. Now just take a minute, make sure I did everything correctly. I think I did. Okay. Okay, now let's see where we land here. Okay, so fortunately, putting in a 0 is not going to matter. So all we have to worry about is that top bound. So this is going to be 2/5 times 4 to the 5 halves. Y cubed over 8. I left that out. Okay, y cubed over 8. So let me put that in. Oh, that's right. I do have a y cubed over 8. Okay, so let me put that in. Put it in order. So this is, now I didn't integrate that, did I? Ah, okay. So this is y to the 4th. I didn't integrate that at all? Ah. Oh, okay, y to the 4th over 32, right? Yeah, negative. And then what about this one? This one was 5 over 24 y to the 3rd. Thank you for pointing that out. Saved me some grief at the end. Now, is everything else correct? 4 times 8, 32. Yeah, okay. So it's looking good so far. Now let's see what happens. Okay, so I'm going to put a 4 in. So this is 2/5 4 to the 5 halves. So really that's 32. Okay, but we'll deal with that in a minute. 5 over 4 times 4 squared is 16. Okay, do that. Minus 4 to the 4th. I'll deal with that in a minute. And then 5 over 24. What's 4 to the 3rd? What, 64 is it? Huh? Okay, so this is 64, and that's going to be 256. Now, did I plug in and got everything right? I'm assuming that's all correct. Okay, hopefully. Okay, now let's see what we've got. We've got 2/5 times, okay, the square root of 4 is 2. 2 to the 5th is 32. Okay, so there's that. Now this is minus 20. Okay, because 16 divided by 4 is 4. 4 times 5 is 20. Yeah. And then what is this one right here? 256 over 32. Now, a 4 will divide out, though, right? Is it 8? So this whole thing is 8 right there? Okay, good, good. And then what about this one over here? This is 64. 64 divided by 12 is what? Is it, well, can we reduce this at all? What do you think? 64 divided by 8? 8? Okay. So this is 8. 24 divided by 8 is 3. So it looks like this is going to be what? 40 over 3? Is that right? That doesn't work out too bad. Okay, so let's see what we've got now. We've got 2/5 times 32. Let me just call that 64 over 5. Whoops. 64 over 5. 64 over 5. and minus 28 plus 40 over 3. Okay. Now it looks like my common denominator is 15. Once again. So let's see, hopefully we'll get what we're looking for here. So this is 3 times 64 minus 15 times 28 plus 5 times 40 over 15. Now what does that all turn out to be? So what is it, negative 28? Same thing. That's the same thing as what we got by doing it, this seems like the long way, right? They both seem like a long way. This just shows you how to apply Green's theorem. Okay? Any questions about that?